Alright, so in this video I'm going to be talking about the particle in a two-dimensional box, or essentially just a two-dimensional infinite square well. So basically what we're going to have is we're going to have an extension of the problem we solved in the previous video, which was the particle in a one-dimensional box, or simply the one-dimensional infinite square well. So we had our x-axis, and basically what we had was that we had an infinite potential that was going to infinity, and basically our particle was enclosed between those two potential barriers, and it went from L to Lx, so that was the length of the box in the x direction. So now what we're going to do is we're going to have a three-dimensional form of that. So we're going to have an infinite square well that is actually going to go in the y direction as well. So we're going to have a length y, and it's going to go from 0 to Ly. So we're going to construct an infinite square well that is going to look like this, and then obviously our potential is going to be a function of both x and y. So now that we have constructed this, what we're going to do is, you can imagine that these are four walls that are enclosing the wave function, and now it's going to be a surface. The wave function is no longer a curve, but it's going to be a surface confined within this particular box. So it is going to exist here. And now what we're going to do is we're going to formulate the Schrödinger equation based on the following boundary conditions. So we're going to have the following boundary conditions. We're going to have the wave function at the points. So let's have 0 should be equal to Ly equal to 0. So that means that the wave function cannot exist outside these boundaries along the y-axis, and also the boundary condition 0y equals to the wave function Lxy equals to 0. So those are our four boundary conditions. So we're going to have this rectangular kind of fence built around it. And now the Schrödinger equation is going to become, we can just derive it from 2m. It's going to be two partial derivatives. The first one is going to be with respect to x plus just like that. And now we're going to have plus our potential Vxy and this is going to be equal to the energy. So this is going to be equal to the energy levels times the function, the wave function of x and y. Now remember, because this is the time independent Schrödinger equation, what we're going to end up having is an expression where whatever values we find here for a wave function, we're going to get the eigenvalues of that equation are going to be the energy levels. But remember, the energy levels, we should expect them now to be a function of both the lengths in x and lengths in y, because we found in the previous problem that the energy level for, or the energy levels for n integers was given by n squared pi squared Planck constant squared over 2mL squared. So obviously we should expect this energy for this particular problem to be dependent upon both lengths. And we're going to take the more general case in which both lengths are different. So that's what we're going to be focusing on in this problem. So we want to confine this to the box, into the space inside of these four walls. So that means that we can ignore this, because we know that the potential is going to be 0 within those four walls. So in the end, our equation is going to be the following. So we're going to have the two partial derivatives, and this is going to be equal to the energy times xy, just like that. And in order to solve this equation, what we're going to apply is the method of separation of variables for partial differential equations. So in this simple example, we're going to assume that the solution is separable in the following way. So we can write two distinct functions of one variable, and then the product of those functions is going to give us our solution. So this means that second partial derivative of this wave function with respect to x is just going to be the derivative of that x function, and then the partial derivative with respect to y is going to be y double prime. And then what we're going to do is we're going to substitute for those in here, so we're going to get h squared over 2m times x double prime y plus xy double prime equals to e times xy. And now we're going to divide both sides by this same function, so we're going to get, I'm going to move this to the other side now, so we're going to get x double prime over x plus y double prime over y equals to minus 2me over Planck constant squared. So now, because we have separated this into a sum of ordinary differential equations, what we can do is we can set each of them equal to some constant. So we're going to set this equal, because remember, if the sum of them is a constant, then that means that each of them has to be a constant. So that's the reasoning behind this. So let's call this constant kx squared. And let's make it negative just for now, so that when we separate this, we're going to get the following: x double prime plus k of x squared x. And obviously the only solution to this, based on the characteristic equation, because we're going to get complex roots of the form r minus I kx, r plus I kx, is going to be a sum of cosine and sine functions. And you might be wondering, why did we make this negative? What was the reasoning behind it? Well, we know for this problem, based on the boundary conditions that we imposed, that the only non-trivial solution has to be the one that has complex roots. And we could show that by doing the whole thing, but that's just common knowledge from differential equations. So we're just going to say, look, based on the boundary conditions in this problem, we know that the only non-trivial solution is going to be this. So we're interested in actually writing out what the solution is going to be. So the general solution is going to be a cosine of kx x plus b sine kx x. So that's going to be our general solution. Now to find the constants, we apply the boundary conditions. So we had the first boundary condition, which was 0, y. This is the same as saying x at 0 is equal to 0. So if we put 0 in here and 0 in here, we get a. This becomes 1, that becomes a, so a is equal to 0. That means that this term doesn't actually exist in the solution, we only have this term. And now the second boundary condition is wave function at Lx y is equal to x of L equals to b sine kx Lx. So that should be Lx there, just to differentiate it from the length along the y direction. And then, because we don't want b to be 0, because that would make our entire solution 0, we need to make this equal to 0. So this kxlx term should be equal to an integer multiple of pi, an integer multiple of pi that is equal or greater than 1. Because remember, if we have an integer of pi that is 0, for example, then the whole solution becomes 0. So that's just not what we want. So we need to have the following condition: kx is going to be equal to nx pi over lx, where nx is going to go from 1, 2, 3, and so on. So that's going to be the definition of that integer. Alright, so now that we have that, we can proceed to write down the actual particular solution for this problem. So we're going to get equals to b sine of nx pi x over lx But now we encounter a little problem. So what is B? B is a normalization constant, just in the same way that we found the normalization constant for the one-dimensional case. We're going to find it for this one. So all we need to do is we're going to integrate from minus infinity to infinity of the square of this function, so absolute value squared. And we're going to set it equal to 1 such that we can actually solve for that constant B. And this is exactly the same problem that we solved last time. So we know that this term is going to be root of 2 over Lx in this case, because that's just what we call the length. So this is going to be the particular solution to the problem. And the reason we can do this kind of thing is because remember that our solution, we're assuming that the solution for our wave function is separable. So if it is separable, it means that we can find normalization constants for both x and y independently of each other. So we're going to get the following. So that's our x, function x. So what about the function y? Well, we can apply the same logic. We can have the differential equation minus k squared of y. And this is going to give us the solution y of y is equal to a cos ky y plus b sine of ky y. And because the boundary conditions are pretty much the same for y as we had before, we know that y should have the following solution. Hopefully it isn't too hard to see the connection between these two, that the two functions should be exactly the same, except for the Lx and Nx terms are going to be different. Obviously the variables, so we're going to have 2 over Ly, and you can show this by yourself just by going through the entire procedure of finding the normalization constant and all that. So that's an exercise for you to do. And we have ny pi y over Ly. So that's going to be our solution there. And that means that our final general solution for this problem, or particular solution I should say, is going to be x times y, which is going to reduce to Lx Ly sine of nx pi x over Lx times sine of ny pi y over Ly. And this is going to be the particular solution to our problem. So the interesting thing about this is that if you know we have two lengths, right? But we also have integers here that are independent of each other. So what this means is that we're going to have an infinite set of solutions, and for each combination of different integers, nx and ny, we're going to get a different solution. So we could have something like this. We could have something like the wave function 1, 1. That means that we input 1 and 1 here. That's going to be one solution. But similarly, we could have 1, 2, which means we put 1 into nx and 2 into ny. That's going to be another solution. And then all the way, and we're going to have also 2, 1, 2, 2, and so on. So the infinite number of solutions just became even larger because we have all these different combinations that we can work with. And what do you think about the energy levels? What do you think the energy levels are going to look like for this particular function? Well, we know that we have these two terms. We have nx and ny, and we have two lengths. So by drawing an analogy with the one-dimensional case, we are going to have the following energy levels. So we're going to have E of nx, comma, ny, because remember we're going to have energy levels that correspond to each of these functions as well, equals to the following. So we're going to have pi squared Planck constant squared over 2m. So those terms do not actually change, but we're going to have nx squared Lx squared plus ny squared over Ly squared. So the energy levels are going to be a sum of those two energy levels. The energy levels for in the x direction and the energy levels for y. So that's what is going to go. And the interesting thing about this is that we can extend this very easily to the three-dimensional case. So let's have a look at the actual particle in a three-dimensional box. And that one can properly be called a particle in a box because it is going to be confined in all three directions. So we're gonna have a box like this, z, y, x. So let's have length x, length z, and length y. So we're gonna construct a box. It's not going to be a cube because we can have different lengths, and then the particle is going to be confined within those, and that's mainly because the potential is, we have a potential barrier in all those directions. So for this problem, which would have the Schrödinger equation of the form, so I'm just gonna use shorthand notation here, plus y plus, or actually I'm just going to use the following one, the more proper notation for this. So let's just use the xx plus yy plus zz equals to e times wave function. So now that means that our wave function of x, y, and z should be something similar to this, but now we have three functions because we're separating this into three functions. So we should get the following. So remember, in the first problem we had 2 over Lx. That was one of the constants. The second normalization constant was Ly, and then the third one should be this, right? Because we're using symmetry to solve this problem. So if we multiply all of this together, we're going to have 2 root 2 over root of Lx, Ly, Lz. And we're going to have three sine functions. So the first one, nx pi x over Lx, sine ny pi y over Ly. And finally, we're going to have sine nz pi z over Lz. So this is going to be the solution to the particle in a three-dimensional box using the same boundary conditions that we have been using for the one-dimensional and two-dimensional case. And as you guessed it, the energy levels, the discrete energy levels, are going to be a function of all those integers, so nx, ny, and nz, which means that we're going to have the following: pi squared, Planck constant squared over 2n, nx squared over Lx squared, plus ny squared over Ly squared, plus nz squared over Lz squared. So we solved this without actually having to go through the entire process, because we know that it's going to look like this based on the fact that the problem is just an extension of the two-dimensional case. So hopefully you have understood the whole procedure, and this is basically what you do with the particle in a box. And there are ways to solve this by finding eigenvalues and eigenvectors using matrices and numerical methods. So that's something that I will do in a future video. But for now, this is basically how you derive those solutions analytically. And remember, the Schrödinger equation is not solvable for most systems. Remember that we're dealing with a single particle. So far, we have been dealing with a single particle. And not just that, we have been dealing with a time-independent Schrödinger equation. So things are going to get quite complicated from here. But we're going to look at some important one-dimensional examples, such as the finite square well and the potential barrier, which explores quantum tunneling. And hopefully those one-dimensional examples can help you understand a little bit more about the physics, about what's happening with all these systems, because it's quite an abstract thing to explain quantum mechanics, because it's very mathematical in its formulation. It's not like classical mechanics where you can explain everything visually and everything is sort of intuitive. When it comes to quantum mechanics, you need to do the math in order to catch a glimpse at what is actually happening. So we're going to continue with more problems like this based on the Schrödinger equation in the following videos.